very much for the thank you all for having me here, and I'm really grateful to you all coming because I know there was a great snow last night. I'm happy to be here, and I'm happy to see you all here in this room. Yeah, today I would like to tell you, a tale of two topology and related quantized transport effect, just to make myself look like someone that would like to actually I do like to collaborate with experimentalists, and I do care a lot about experimental effects. So not just about the deep fundamental question about topological phases of matter, but also how do they reveal themselves in actual experimental setup. And so I will talk about two quantized transport phenomena that brings together two ingredients: topology and superconductivity. But just to begin with the big picture, because I know some of you are not working on condensed matter, let me begin with food. We just grabbed lunch. I hope you're not too hungry at this moment. As a condensed matter physicist, I think it's our rightful duty to classify all kinds of matter, including baked matter. So if you go to a bakery, you may be served with a diversity of pastry. So I'm from Hong Kong, so I like to talk about pineapple bun, which is topologically a sphere. Here in America, we can't avoid talking about donuts. See that in Dunkin' Donuts, and torus with genus 1. And if you're from Europe, I have the impression that people like pretzel there. And you can have all kinds of genus. This is genus 2 torus. You can have genus 3, genus 4 torus. And if you're in a bakery, which is maybe very crowded, you want to communicate efficiently and safely to the people in the counter serving you the pastry what kind of baked matter you want. Maybe the best way is to look at the topological structure of this pastry. If you say, I want a genus G bread, then you will be unambiguously served this pineapple bun. If you want something genus 1, you will get the donut. So topology really provides a robust way for storing, processing, and also communicating information. And that would be particularly useful under the assumption that the people working in the pastry is physics or math graduates, and which is likely the case nowadays, assuming that hopefully they're just working part-time there out of good faith. Mother Nature is also a nice bakery that provides a lot of kinds of topological phases of quantum matter. And one big factory or large systems where you find different topological phases is a fractional quantum Hall platform, fractional quantum Hall systems. And you see this, and they come with a quantized transport signature. So here, this is the vertical axis is the Hall resistance plotted as a function of magnetic fields. And you can see this very robust plateaus happening at different magnetic fields, which corresponds to different filling fractions for the electrons. These plateaus corresponding to this quantized transport signature, they are representing a topological phase of matter. And this plateau is like the holes in this pastries they can see. They don't just have quantized transport signature. In fact, if you look at the gap excitations, these are something called anyons, whose braiding can be used to encode logical information in a robust way. And by braiding, you can process those logical information immune to this perturbation and disorder. And that gives rise to the whole field of topological quantum computation. And also it can provide a way for robust quantum memory. So a topological classification of matter is not just interesting, entertaining, but is also very useful. And in today's talk, I would like to focus on quantized transport effect, because that is something that is arguably easiest to measure in the lab for experimentalists to probe the existence of these interesting exotic phases of matter. And I think it's also timely for us to combine different ingredients. In pastry, in bakery, you talk about Asian fusion, different kind of fusion food. So in today's talk, I would like to go along that line too. I would like to study fusion of two important ingredients in modern day condensed matter physics. The study of topological phases is just one main pillar. The other important theme in condensed matter physics is superconductivity. So in today's talk, I would like to talk about two different quantized transport phenomena that arises when you bring topology with together with superconductivity. In the first part, I would like to focus on a topological system that I just talked about, right? The most famous one, fractional quantum Hall states. And this is work done in collaboration with a brilliant graduate student at Princeton, Hao Chan, and Biao Lian, who many of you know, assistant professor here at Princeton. And in this recent work, we study what happens when you introduce superconducting proximity in the presence of disorder to a specific type of fractional quantum Hall system at filling 2/3. In a few minutes, I will explain why we look at this specific filling fraction. We believe that the story I'm going to tell you can be generalized to other filling fractions, but this is the simplest non-trivial filling fraction that has the right ingredients to allow for an interesting interplay between topological effect and superconductivity. And in particular, we're approximatizing this topological system on the edge. And the quantization that I'm going to tell you critically rely on the existence of disorder, randomness. Okay. In the second part of the talk, I'm going to talk about, as Luca kindly introduced, a topic that I am really interested in and is really motivated by my supervisor back at Penn, Charlie Kane, who motivated me to think about topology in metals, topology of Fermi C. And unlike what I talked about like 5 months ago, where we could use equal time density correlation to probe Fermi C topology, today I'm going to tell you about another way to probe Fermi C topology, hopefully making the notion of Fermi C topology even more useful. At least you can see that it can be probed in various different experimental avenues. And here, again, I'm going to combine metal, which is a topological material, as I'm going to convince you in the second part of the talk, via the Fermi C topology. I'm going to combine that with superconducting proximity. You proximatize this topological metal in the bulk, forming a Josephson junction. You will have something called Andreev states. I'm going to talk about what that is. Even from a high energy perspective, you can appreciate that Andreev state is something that you actually are familiar with before, in terms of Jakiv-Rabi zero modes. So I will talk about that. The thing is that using this Andreev state, you can do transport in the direction along the superconductor normal metal superconductor interface. And then that leads to some quantized transport effect that probes the topology of Fermi C in the underlying metal that forms Josephson junction. Okay. So and that work also benefited a lot from collaboration with Christophe Debut, who was a postdoc at Penn, and now he moves on to University of Antwerp in Belgium. So let me begin with the first part, which is some interesting effect that happens when you combine fractional quantum Hall with superconductivity. Why do we want to do that, you might ask, up front? And the reason is that, well, it provides a nice way to engineer exotic anyons. We talked about, you have different kind of fractional quantum Hall states. There are exotic anyons, but exotic anyons are not created equal. Some are better than the other. Some are more useful than the other. If you want to, just by braiding these anyons, realize useful logical gates for computation, you want the kinds of exotic anyons that are hardly realizable in the usual fractional quantum Hall platform. And around 2010, people find new ways of engineering these exotic anyons, known as power fermion zero modes or Fibonacci anyons. These kind of things can be engineered by taking a easy to realize abelian fractional quantum Hall states like nu equals to 1/3 Laughlin states, and combine it with superconductivity. And for example, if you take a 2/3 abelian fractional quantum Hall states and put on it a superconducting island, you can realize excitations that are like power fermions or Fibonacci anyons, and using braiding, you can realize interesting entangling gates for computation, useful for computation. And that is a bulk proximity proposal, which if you're an experimentalist, you may stand up and ask, is it really that feasible? I mean, the ingredient seems to be rather easy to realize. But when you put them together, you say interesting effects come out, great. But when you put them together, is this still a feasible proposal to consider? Fractional quantum Hall states require really large magnetic field. Superconductor hates large magnetic field. So bulk proximity effect actually encounters great experimental obstacles because these are two ingredients that don't like each other. They cannot be easily realized in the same situation.
Aren't there examples now of zero field or near zero field?
Yeah. There's zero field called fractional quantum anomalous Hall, or some people call it fractional child insulator. That gives it's only in the last 2 years that it becomes experimental reality. So that really brings this proposal much closer to reality. Indeed. So yeah, I look forward to seeing how this proposal can be realized in the very near future. Yeah, but I think if you go back, not just 2 years, but maybe 5 years, 6 years, then people are mostly still playing with fractional quantum Hall states, which requires large magnetic field. But that experimentalists are not immediately intimidated by this kind of proposal. They can consider edge proximity. You have a region with large magnetic field, you get fractional quantum Hall. Maybe outside, you can put in a superconductor. But then you're only proximatizing the edge. And experimentally, there have been some results. I'm going to talk to you about it briefly, where they do this. But there are theoretical proposals saying why this is interesting. Again, by proximatizing fractional quantum Hall edge state with superconductivity, you can also realize interesting exotic anion modes localized at the domain wall boundaries. And that here, because you can get out the boundary using 2 different mechanisms, via superconducting pairing or by backscattering. So you can create a domain wall, and the domain wall can trap power Fermi on 0 modes, useful for quantum computation. So that just provides you with the background of why some people are obsessed with combining these 2 things together. And this is also a platform where you might expect novel transport signatures. Okay, so let me invite you to do a thought experiment with me. So imagine you are an electron moving in a quantum Hall system, and we're interested in low energy physics. So you're an electron, not in a gapped bulk region. You're an electron moving on the edge, okay, skipping on the edge. If you use a semi-classical picture, you are just following the effect of Lorentz force. You're just skipping on the edge like this. Okay, so you're an electron moving on the edge, following a skipping orbits. And if I create a junction between a fractional quantum Hall or just a quantum Hall with a superconductor, you skip on the edge and then you hit the superconductor, what can happen? You want to go into the superconductor, right? But superconductor doesn't like single electrons. Superconductor like paired electrons. So what would happen is that a Kuiper pair would go into the superconductor, and then an electron get Andreev reflected as a Hall, right? So you pull in 2 electrons into the superconductor, and then an electron on the edge will convert into a Hall. Okay, a Hall has opposite charge and opposite mass as the electron. So when you do the right-hand rule, think about what happens under the effect of Lorentz force, you appreciate that a Hall would skip in the same direction as the electron. Okay? So motion continues in the same direction, and Andreev reflection happen multiple times. So as a result, at the interface between quantum Hall edge and superconductor, you have some people call it Andreev edge states. You have superposition of electron and holes, and electron hole, they oscillate into each other. You may come out, an electron coming in may come out as a Hall, or it may come out as an electron. It really depends on how many times you hit the wall and bounce back, right? So this thought experiment seems to be telling you that not much universal can happen in this picture. Because if you make the magnetic field larger or you make the electron move faster, then you can change the period and you can change the end result of whether it's an electron or Hall coming out. Okay, but at least there is something, well, I will talk about universality later, but there's something indeed quite novel happening in this picture. If you have electron coming in, holes going out, you can do some transport measurement and measure some negative resistance. Okay, and that is indeed measured in some experiments around 2020. So that's still before the development of fractional Chern insulator. But it would be really cool to see some similar experiments done in the zero magnetic field analog, like Ruben just suggested. But this is an experiment done for graphene quantum Hall. Okay, so this picture is a faithful picture describing this experiment. What they measure is a voltage difference between the outgoing downstream current and the superconductor. That voltage difference divided by the current flowing into the superconductor. That defines something called downstream resistance R to the XX, which is negative if electron comes in and holes go out. If electrons come in and electron goes out, then that would be a positive downstream resistance. And what they see is that when the blue curve, which is the Hall conductance, is quantized, so you're in a gapped quantum Hall regime, you have edge states, then this black curve, which is the downstream resistance, actually oscillates between positive and negative values. So that is telling you, as you change some microscopic parameters, electrons come in, sometimes go out as a Hall, showing as a negative downstream resistance. Sometimes they come in as an electron, showing as a positive downstream resistance. So this kind of oscillation of downstream resistance from positive to negative is a kind of a novel transport signature. which is unique to the quantum Hall edge states in proximity to superconductor. Okay. But the thing is that nothing really universal or quantized happens when you look at this plot. So the first question I want to address in this talk is whether there is some universal quantized transport phenomena that can arise when you put a superconductor next to a quantum Hall system. Okay. And at least this thought experiment, this cartoon picture we just looked at, seems to suggest that a fully chiral edge is not sufficient for the purpose of having a quantized transport effect. So this leads me to talk about 2/3. Fractional quantum Hall states at 2/3 is famous for having a rather complicated edge state structure. It has counter-propagating edge modes. Okay. And this brings me to talk about a theory sometimes known as Kingfisher-Puchinsky theory. And I think it's quite apt to talk about this in Chicago because I know people here like to work between different disciplines, sub-disciplines in physics. I think this is a great example of how a condensed matter people like Kane and Fisher works nicely with Puchinsky and come with some interesting explanation for condensed matter phenomena. So this is about quantized transport, normal transport. So there's no role of superconductivity on this slide for this particular application. They're just trying to understand why there can be quantized transport effect, normal transport, say two-terminal conductance or Hall conductance, why there can be quantized transport for the edge states of 2/3 filled fractional quantum Hall states. So pictorially speaking, on the edge, you have a downstream mode that corresponds to the filling fraction nu equals to 1 integer quantum Hall edge mode, and you have an upstream 1/3 mode. So that is the outset. That is the minimal edge model describing filling 2/3 fractional quantum Hall states. And technically speaking, you can describe that using two components Luttinger liquid theory, okay? Counter-propagating Luttinger liquid theory. You have a term that describes the density-density interaction between these two modes. So I and j take values between 1 and 2. This is the 1 mode, this is the 2 mode, okay? Edge electron can be, if you use bosonization, they are created by this vertex operator. I don't want to go to the technical detail, but if you do a calculation using this model, try to calculate a two-terminal conductance, you'll appreciate that the conductance is sensitively dependent on the interaction parameters. So this Vij is characterizing density-density interaction on the edge. The two-terminal conductance depends on this C, which is a function of interaction parameters. Okay, so this tells you that if you do a two-terminal conductance measurement, you should measure all kinds of values, not just 2e squared divided by 3h. But in experiments, people robustly see 2e squared over 3h. Namely, they robustly see delta equals to 1. So it's a mystery back then why experimentally you measure a quantized value, a universal value. But if you use this edge theory and do an honest calculation for the two-terminal conductance, you seem to conclude that the conductance will sensitively depends on edge interaction. So it's a mystery. Kingfisher-Puchinsky came in and say, well, in experiments, if you want to talk about experiments, in reality, you actually have disorder. You have disorder on the edge, which mixes and scatters these edge modes into each other. So they did a disorder renormalization group analysis and realized that if you introduce randomness on the edge, allow these edge modes to scatter into each other, then at low energy, if you apply low bias voltage and probe at a low temperature, the RG flow would bring this edge theory into a fixed point with two decoupled modes. You have one mode that is completely free, is a chiral free boson carrying charge. It carries charge 2e over 3, and then you have an upstream neutral modes that experience the disorder. So all the complication about randomness is carried by this upstream neutral mode, but at low energy, you have a stable RG fixed point that tells you that a charge mode is decoupled from a neutral mode. And if you do an electrical transport measurement, all you care about is the charge mode, which is free. And that gives you a quantized two-terminal conductance that does not care about the precise interaction on the edge. And this is kind of experimentally verified in some recent, not too recent, but 2010 experiments from Weizmann Institute. So they measure the existence of, well, the quantization of the two-terminal conductance has been measured even longer ago, but the existence of an upstream neutral mode has been probed in some short noise measurement by the Wiseman. So that is some prehistoric background, trying to say that how Kingfisher and Puczynski came in together and use some disorder RG understanding to explain quantized transport phenomena, and that is in a normal non-superconducting context. And now over the years from a background introduction, you can appreciate that there's some interest of combining fractional quantum Hall with superconductivity. So now let's see what interesting new things we can learn by combining a superconductivity with fractional quantum Hall edge like this. So first of all, let me give you a little more details of what Kingfisher-Puczynski is really doing. They are adding this vertex operator, this term that describes backscattering, into their theory, right? So as I told you, the Bose-Nice description of the Luttinger liquid on the edge is that an edge electron can be created in two ways, e to the power I phi 1 or e to the power minus I phi 2. So this operator is charge neutral. It doesn't create any particle. It just scatter one mode into the two mode. Okay. So and this gives you the and you can repackage this field as a neutral field. It doesn't carry any charge. Now, in the presence of a superconductor, you can imagine many more terms, because a superconductor would, in a sense, breaks particle number conservation. The superconductor offers you as many Kuiper pairs as you want. It's a condensate of Kuiper pairs. So the edge can tunnel in and out Kuiper pairs between the superconductor and the fractional quantum Hall edge. So in principle, you should allow, for example, you should allow yourself to consider a Kuiper pair tunneling term like this. You should be able to consider adding this term into your Lagrangian. Okay? And actually, you have infinitely more terms than this that you can consider adding into your Lagrangian. Generally speaking, all these operators with integer q and p, integer q is telling you how many Kuiper pairs this operator creates. Integer p is telling you how many backscattering you're doing on the edge. A vertex operator that respects locality and fermion parity conservation would take this form, and they should generally be allowed to consider be added into your Lagrangian. Okay. Now you think, okay, well, it seems to be a complicated problem because I have many terms that I should consider. But the thing is that we should only consider things that are relevant, right? Both in the literal sense and the RG sense. So the things to do is that the scaling dimension of this operator, it can be easily calculated in terms of the density-density interaction between the edge. If I call that interaction parameter G, which is a function of this Vij, and recall that from previous slide, Vij is really parameterizing the density-density interaction on the edge. That defines an interaction parameter G, which controls scaling dimension of operators parameterized by Q and P. Okay. You don't need to load this into your brain. I just want to tell you that when you have counter-propagating edge modes, scaling dimension of any vertex operator is, so first of all, it's not universal. It's not universal. It can be tuned by interaction. And in fact, it is also this scaling dimension that appears in the previous clean edge calculation that tells you two-terminal conductance seems to be non-universal. Okay. Now, the thing is that because scaling dimension can be tuned, you would ask yourself, well, when my interaction is at some point, what are the operators that are relevant? And I keep them, and I throw away all those that are irrelevant. Okay.
It's G0.
Yeah. Sorry.
What is G0?
Yeah, G0 is it's a numeric value. It's 2 plus square root of 3 raised to square. So it is basically when G equals to G0, the neutral backscattering operator is relevant and has scaling dimension 1. It is a specific fixed point corresponding to the Kingfisher-Puczynski fixed point. Yeah, but its precise value here is not that important. But if you ask me what is that value, G0 is the critical value of G where this operator has scaling dimension 1. Yeah. So we don't need to really load all this into our mind, but the thing is that if you use that expression, you can appreciate that, first of all, for any pairs of QP, which fix a vertex operator you look at, the scaling dimension is a convex function of the interaction parameter. So there's a minimum value. Now you can, of course, find that minimum value by going through some tedious algebra, or you can take a different perspective. You can say the following thing. Well, the minimal scaling dimension of an operator corresponds to its conformal spin. Its conformal spin can be easily deduced by looking at this operator. So I have from here, I can see that its right moving conformal spin is 3q squared. And because I have a right moving mode that is a downstream moving mode phi rho, and I have an upstream moving mode that is phi sigma, which gives me the conformal dimension of the other direction, which is p squared. So the conformal spin is basically 3q squared minus p squared. That can be rather easily written down. And the conformal spin gives you the minimal scaling dimension. It is not something that you can tune by interaction. But if you tune the interaction to change the scaling dimension, the minimal value it can be realized is basically this. And the condition for an operator to be relevant under disorder and the randomness is for the scaling dimension to be smaller than 3/2. Okay. And then that basically tells you that if you want to list out a set of operators which can ever be possibly relevant, then you should be solving this kind of equation, asking yourself whether p squared minus 3q squared can be equal to 1. So if it can equal to 1, then for some value of interaction, you can make that operator relevant because we can make that operator have scaling dimension smaller than 3/2. Okay. And this in number theory is known as the Pell-Fermat equation. Turns out it has infinitely many solutions. So this is telling you that you have infinitely many different operators whose scaling dimension, minimal scaling dimension, can be smaller than 3/2. In particular, that equals to 1. Okay.
Sorry, any question? So the condition for it to be relevant before this order would be delta smaller than 2?
Yes, exactly. For clean edge, it will be smaller than 2.
That's easier. You first become relevant without disorder.
Yes. But I want to consider a situation with disorder that and that gives me delta smaller than 3/2. Yeah. Indeed, if I have clean edge, then I compare the scaling dimension with space-time dimension, which is 2 in this case. Yeah. But with disorder, by disorder I mean short-range correlated in space, a type of disorder obeying a zero mean Gaussian distribution. That would correspond to having a scaling dimension smaller than 3/2. That can be if you want me to go into detail, I can go to that.
But I guess I'm wondering, why do you need disorder in the sense that these same operators would have been relevant without disorder? I guess you need something to break translation so that you don't have that extra U1 symmetry, so that you can put them in the action.
That is also another reason that we want.
But you need the randomness of disorder.
Let me see. Right. So if I do not have disorder, I don't have universality. That is at least what Kingfisher-Puchinsky taught us. If you just consider this situation, for the edge to flow to a decoupled fixed point with a universal quantized two-terminal conductance, you need randomness, you need disorder. Because at the fixed point, randomness would guarantee that the coupling between the downstream charge mode and upstream neutral mode is RG irrelevant. That seriously, critically relies on randomness. Yeah, and we want to generalize this in the presence of superconductivity. So that's why we also assume the superconducting proximity effect to be random. If nothing's random, we generally do not expect any universal physics arising. The universal physics arise from having randomness. Yeah, so that's why here I compare my scaling dimension to 1.5. Yeah, and indeed, if you work under the assumption of having disorder, which I think is experimentally a rather favorable situation as compared to assuming clean edge with uniform pairing, then depending on where your interaction value is, you will have different operator that is relevant, and you can play the same story as Kingfisher-Puchinsky did and see that you have a downstream mode that is free, a chiral boson, and an upstream mode that experience the disorder. The difference is that generally speaking, both modes would carry charge, But the same thing as in Kingfisher-Puchinsky is that randomness guarantees that as long as one of these operators is relevant, the edge would flow to a fixed point where you have two modes that are decoupled. The random modes would be averaged out and do not contribute to electrical transport. The charge mode, the other free chiral boson carrying some value of charge, depending on the solution of Pell-Fermat equation, that will contribute a quantized transport signature. So that is the theory that we have for predicting new edge phases and also the quantized transport signature.
Sorry, I'm not sure if this matters. Is the randomness only in this superconducting region, or is it everywhere? Or
Yes.
just,
So here I'm just talking about an interval, a segment of the edge, and try to describe what it looks like. Next, I'm going to talk about what happens when we try to predict transport signature. Then the region proximatized by superconductor, we assume will flow into one of these phases, assuming you have the ability to tune the edge interaction so that you can flow to different fixed points. And then the rest, we assume it is in a Kingfisher-Puchinsky one, which I think is a reasonable assumption because they measure normal transport that is described by the Kingfisher-Puchinsky theory. So the rest, in proximatized regions, it's dominated by neutral backscattering. The region proximatized by a superconductor, we assume it is dominated by some sort of superconducting disorder, superconducting pairing, proximity. Yeah. So maybe the first thing I want to say is that this tells us that by proximatizing the fractional quantum Hall edge with superconductivity, there's actually an infinite family of novel edge phases. And these phases generalize the Kingfisher-Puchinsky theory. Each of these phases is a phase because it's described by an interval of interaction parameter. As long as you're in this interval, then this disorder superconducting proximity operator will be relevant and will drive an RG flow to the fixed point value. And your edge will be, at low energy, will be characterized by that fixed point theory where you have two decoupled modes. One is free chiral boson carrying some charge 2p/3, and you have another upstream mode that generally carries charge but experience randomness, and its random rotation would average it to 0 and not contributing to electrical transport. So an experimental setup that allows you to probe for the existence of these new phases will be an experimental setup that is similar to the Finkelstein experiment that I just talked. I try to motivate you to think about in a thought experiment. You measure a voltage difference between a downstream segment V2 with respect to the superconductor voltage V3 and divide that by the currents flowing into the superconductor. That defines a downstream resistance. And you can compute that, solve a scattering problem, because in one segment it's described by the Kingfisher-Puchinsky theory, and then in the superconducting segment is described by one of these new fixed points that we predicted, and that will lead to a calculation of the transmission probability for you to come in as an electron, going out as a hole, and that gives you a quantized downstream resistance, which is a characteristic of these new edge phases that arise when you put fractional quantum Hall edge and superconductivity, disorder superconductivity together. Okay. There are ways to generalize this. Importance of the theory here is that you have counterpropagating edge modes, so that scaling dimension is tunable by interaction, and that allows you to explore the existence of multiple different new phases. Counterpropagating edge modes appears in many different places, not just in 2/3 case. There's a bunch of Jane states which have counterpropagating edge states, and also famously is anti-Pfaffian non-abelian fractional quantum Hall states studied by Professor Mike Levin also have counterpropagating edge states. In particular, you have counterpropagating Majorana fermions, so that would add to a new level of complexity to the theory I just talked about. It will be interesting to explore what kind of edge phases, new fixed points, and corresponding quantized transport signature that can arise in this setup. So when you proximatize this Pfaffian states with superconductor, what kind of new edge phase can appear? And maybe there's some potential application to FCI as suggested by Ruben. And I started out talking about negative downstream resistance. So if you have electron coming in and mostly holes going out, you should expect to have negative downstream resistance. But in our theory, we've seen something quantized, okay? But the quantized values is always positive. So it raises the question of whether there are interesting effects with negative downstream, quantized downstream negative resistance. We haven't been able to find any of these yet, but it would look great to look for some to further this investigation to see whether there are examples like that, and whether there's some interesting connections to parafermions, which I started out talking about. These are all interesting things that will be good to look at.
Yeah, just a question on your previous slide.
Yes.
If I understood correctly, like this scattering problem is important, like the transmission and reflection coefficient from this particular scattering problem from the
Yes.
two different edge theories. So my question is, how much does the answer depend on exactly that interface between the superconducting region and the non-superconducting region? Like, for example, suppose I put like a little, suppose it like did something more complicated, like it alternated from, there's like a small region inside the superconductor that's described by the Kane-Fisher-Polchinski, and then went back to superconductor. In other words, you had like yellow, short blue, short yellow, and then bigger blue. Would that change the? I'm trying to understand how the dependence on the details of that interface. Like does it just matter that I have blue to the right and yellow to the left, or if I change exactly what happens between the yellow and blue, would it change your answer?
I think that's a great question. So we calculated this downstream resistance under the assumption that in the blue region, I already flow to the fixed point. So I have decoupled modes of phi d and phi u, which is expressed in terms of phi 1, phi 2 in some ways. And of course, in Kane-Fisher-Polchinski, you have phi rho, phi sigma, which is also related to phi 1, phi 2 in some ways. And it is important that I assume that in the yellow region, I'm in the Kane-Fisher-Polchinski fixed point. In the blue region, I'm in this new superconducting fixed point. If the interval is not long enough, then I don't think I am justified to assume that I'm at a fixed point. I need to assume that my superconducting interval is long enough. So if I'm probing long range physics, I can assume that both regions, they are individually in their fixed point Lagrangian, and then I can write down boundary condition matching to solve the scattering problem. So that is how we obtain this scattering transmission fraction. So if this length is too small, then yeah, it generally be a complicated problem. We're working under the assumption that all the regions are long enough so that individually they are described by a fixed point Lagrangian. Yeah.
I have a dumb question. So for this nu equals 2/3, why can't I have two modes propagating in the same direction, like two 1/3 modes in the same direction?
So the understanding of fractional quantum Hall is that at filling 2/3, it is not described by co-propagating 1/3. Well, of course, you may think that 2/3 is like two copies of 1/3. So why not two co-propagating? The thing is that this fractional quantum Hall is realized by fractionally filling lowest Landau level. Lowest Landau level has a particle hole symmetry. And so the boundary between 2/3 and vacuum, which is nu equals to 0, it's under particle hole transformation. It's really under this transformation is like nu equals to 1 and nu equals to 1/3. So the boundary actually have counter-propagating edge modes. Yeah. Yeah. But I think in early 90s, this is actually a mystery. What is the edge structure of 2/3? People have this understanding from particle hole symmetry that motivates people to think of the counter-propagating edge structure as the more correct state. Yeah, which is later on verified by some numerics.
Your disorder is zero mean, right?
Yes, I need to assume that my disorder is zero mean.
Well, why is that the right thing to do? You might expect it to be more relevant if it has a mean.
Yeah, if it has a mean, then that part would. I think this thing would become more complicated. It would be if I don't have disorder, I just have a uniform value.
Yeah.
Then then I think it's just that I don't know what to do with that in order to get some universal transport signal, quantized transport signal. Yeah. So for me to for quantized transport to work, I need to assume a zero mean randomness. Yeah. I think it's interesting to think about what happens when I have a non-zero mean. Yeah.
The two modes have different momenta though, right? So these scattering terms naturally will be, I don't know what it would mean for it to be uniform. It would mean like you have some tunneling that exactly is commensurate with the difference in the two momenta.
Yeah,
Yeah, it needs to break translations, but it's like
In a very special way.
in a very
You have to
special way, yeah.
break it perfectly commensurate with the momentum difference for it to be one.
And yes, yeah. And also, I think if you have some chemical potential disorder on the edge, that can also be translated into randomness in all the vertex operator. Yeah. So I think there are many origins for randomness to occur here.
But so you had this collection of vertex operators.
Yes.
You have some new ones that are allowed thanks to superconductivity.
Yes.
Is any of them allowed by translation invariance?
Is any of
Or are
them
they all charged
allowed?
under?
So I think in principle they can be allowed by translation invariance actually, because this operator would corresponds to, it's roughly speaking, it's like it's basically psi1 psi2, right? Psi1 psi2, and psi1 psi2 maybe they can be at the same well, how to say that? Psi1 psi2.
Yeah, that's allowed by translation invariance,
Yeah.
but not by U1. So that one, yeah, why couldn't that one have a zero mean? I mean, it doesn't. That one seems like it's.
I think it's generally a great question to consider. What happens when I have some level of uniformity and on top of it I add in disorder? Yeah, that's a more complicated question that I don't know how to analyze at the moment. Yeah. So disorder seems to be causing some trouble here for my explanation. At least the simple story I can tell is that if you let me assume a kind of randomness with zero mean, then I can play the same story where Fisher-Puchinsky did for normal transport and get some new superconducting phases enabled by disorder superconducting proximity with some quantized transport signature. So let me not talk about the second part where I absolutely do not want disorder. Okay. In this part, the topological system that I'm interested in is two-dimensional metal. A two-dimensional metal, and let me assume here I don't even have interaction, is a free Fermi gas problem. The ground state of this metal is described by the Fermi C, which I shaded in green here. If you have an electron pocket, then the Fermi C topology would have a topology of a disk. If you have a whole pocket, and then the Fermi C topology is really a torus minus a disk. And you can distinguish that by the Euler characteristic, which in one case is 1, the other case is -1. So this is the kind of Fermi C topology I'm talking about. And the question I want to pose here is, how do we extract this topological invariant? Turns out there are different ways to do it. You can look at it using equal time density correlation function, which I'm not going to talk about in today's talk. I want to talk about transport signature associated to Fermi C topology. And that requires me to think of a setup like this. So you have a two-dimensional electron gas, you proximatize it into a Josephson junction. If you do a non-local current measurement in the direction along the interface, you can also get a quantized transport signature. But before I talk about that, let me invoke your understanding of a simpler problem, which has a lot of similarity to this problem. and that is one-dimensional quantized transport in quantum wire. Okay. We probably learned about that at some point in StatMech. Some of probably forget about it, so let me quickly review the physics here. You have a quantum wire, so you have some one-dimensional electrons moving in the x direction. And maybe you can describe that using this kind of energy momentum dispersion relation. So if you feel your chemical potential here, you have two channels. Okay? You have two channels of mobile electrons. If you apply a bias voltage on the two ends of the quantum wires, you create a chemical potential difference. You have more right-moving electrons than the left-moving electrons. If you count N times E times V, you'll realize that the current is proportional to voltage difference, and the coefficient is quantized by the number of channels that you partially occupy. And here, let me call it chi-f for the reason that later on I'm going to generalize it to two-dimension. But here, this number is just counting number of partially occupied bands. Here is 2. Okay. And so this is the Landauer conductance related to quantization of quantum transport in one dimension. Now, of course, here I need to assume that my quantum wire is completely clean, ballistic, so that I don't have any backscattering. If I have backscattering, then this conductance wouldn't be perfectly quantized to integer. It will be proportional to the transparency of the wire. But so it's less robust than the quantum Hall transport, a quantized Hall resistance that you see in the first part of my talk. But it doesn't mean that it is completely insane for experimentalists to realize this. In fact, in various experimental platforms, people have seen this kind of quantized transport phenomenon related to Landauer transport. For example, you can see that in quantum point contacts. So instead of having a wire, you can imagine that the wire can be realized by a quantum point contact. So electron is moving in this direction. If you make this quantum point contact very, very small, you're just allowing a few channels of electrons moving through this quantum point contact. And you can change the gate voltage, make the quantum point contact wider or narrower, then you can change the number of channels. Okay, you can see the step structure. You can also do it with nanotubes, semiconductor nanowires. So in the second part of my talk, I know I don't have much time left, but I want to generalize this to higher dimension. And to be able to do that, one needs to ask the question, what is this chi-f really telling us? In 1D, this chi-f counts the number of Fermi points, or count the number of connected components of the Fermi sea. So if you ask a mathematician to interpret this chi-f, they will say it's really the Euler characteristic of the one-dimensional Fermi sea manifold. This notion can be generalized to higher dimension. In 2D, this chi-f, you can introduce a topological invariance, which I also name it chi-f, which counts Fermi surfaces. But Fermi surfaces in 2D come in two flavors, right? You have electron pocket, you have hole pockets. So it turns out the right way, which is consistent with how mathematicians would define Euler characteristic, is to count the electron pocket as +1 and count the hole pockets as -1. Okay, so a 2D Euler characteristic of Fermi sea Euler characteristic would be counting the number of electron pockets minus the number of hole pockets. I can show you offline more rigorously how this definition is consistent with, say, B minus E plus F, or alternating sum of Betti numbers, how you would really generically calculate Euler characteristic for any two-dimensional manifold. But this is, trust me, that this is one way to define Euler characteristic, which is consistent with the general mathematical definition. But this is a more physically motivated way, counting number of Fermi surface points. Yeah.
So can you say also for the 1D case, is there like a 3 and a 2, or for this 1D case? So sorry, on the top of the slide.
Yes.
So
yes.
I have 2 gray guys.
Yes.
Is that correct? And then
yes.
3 white. Or how do I count in one?
Yeah, because this is my Fermi sea. The Fermi sea is the gray guy.
Right.
I put my chemical potential here, so this is my Fermi sea. If I move my chemical potential up, then this would be my Fermi sea. So you see, if you count the number of components of the Fermi sea, you can
right.
Yeah,
but
you get a topological invariant, right?
Are there any holes I should count there, or am I misunderstanding?
Sorry?
Are there any hole Fermi seas I should count in the 1D case?
So yeah. So in the 1D case, the hole pocket and the electron pocket really is topologically equivalent. So hole pocket in 1D So an electron pocket would look like this. A hole pocket would look like this, right? So this is my boundary of Brion zone, right? But if you shift a little bit, shift the center of Brion zone to here, then you will see that the Fermi sea looks the same. So in 1D, there's really no distinction between electron pocket and hole pocket, but in 2D there is. So an even more useful way to count order characteristic is to look at property on the Fermi surface, because in 1D, instead of counting how many Fermi sea you have, you can also count how many pairs of Fermi points you have. And the Fermi points is what is related to low energy transport, because when you create bias voltage, you're populating or depopulating states around the Fermi points. So indeed, in 1D, you can just count how many pairs of Fermi points you have. And in 2D, you can count number of critical points that you have on the Fermi surface. And I can define the critical points by specifying a reference direction, and let me call this as the x direction. And I can look at points whose Fermi velocity is completely parallel to this x direction. That's how I define critical points. And there are two types of critical points I can define: a convex one, like the red one, or the concave one. Okay. So if you count the convex one as CE and count the convex one as CH, then the difference between these two types of critical points on the Fermi surface would give you the order characteristic. For example, this is 1 minus 0, this is 0 minus 1. This one is 1 minus 1, which is consistent with the fact that order characteristic of an annulus shape is 0. Okay. And to appreciate that this is really a topological invariant, you can take this one and pinch it a little bit and look and get this shape. Now the counting of critical point changes, but the difference is unchanged. So that is just reflecting the fact that this and that has the same topology, order characteristics plus 1. So that is the math. And I've connected it to some properties on the Fermi surface. So now I try to move one step further and connect critical points on the Fermi surface to some physics, so that experimentalists can do transport and measure some properties related to this critical point and extract chi-f. Okay. So now I take a 2D metal that I like, and I have some Fermi sea topology that I want to probe. And let me lay down a Josephson junction on it. Okay, so I proximatize the top region with superconducting order parameter plus delta, and the lower region it's minus delta. So this is a pi junction because my superconducting order parameter changes sign. There's a pi phase shift. And it's kind of well known in this community studying Josephson junction that this would give you an in-gap, a zero energy Andreev states. You can understand that as a consequence of Jakiv-Rabi zero modes. The physics is described by so-called BDG Hamiltonian, Bogolubov, the Jeans Hamiltonian, which take this form. So what I'm doing here is that I assume I have translation symmetry, just for the sake of argument. I have translation symmetry in this direction. And for each value of kx, I can linearize my dispersion around the Fermi surface. So this is the linearized normal Hamiltonian part. But because I have a superconducting pairing potential, I also, in the BDG Hamiltonian, I have a Dirac mass term. This Dirac mass is corresponding to the superconducting pairing potential. And because my pairing potential changes sign, the BDG Hamiltonian is really describing a Dirac Hamiltonian with a sign changing mass term. As you go from top to bottom, the mass changes sign. Okay. So this interface would thus trap a Jakiv-Rabi zero energy mode localized at the interface. Now that is the argument that you can play for you to understand this Andreev states trapped at the SNS interface. But you can only play that argument when you linearize around the Fermi surface. And you can no longer linearize around the Fermi surface if your momentum is close to the Fermi surface critical points. Okay. So as a consequence, it's only for values of momentum deep inside the Fermi sea, away from the critical points, that the corresponding Andreev states is at zero energy. And so as a function of kx, it's not dispersive. But if you're close to the critical points, the energy is actually non-zero. So as a function of k, in general, the Andreev states actually would have a dispersion. Namely, it should move along the junction. Okay. And depending on whether this is an Andreev state associated with a convex critical point or a concave critical point, if you study the particle hole nature of these Andreev states, you will see that it's either like an electron or like a hole. Okay, so let me consider a case where you have a convex critical point. The corresponding Andreev down state dispersion will look like this. Okay, if you're in the middle of the junction, you're some superposition of electron and hole. So I make it look orange or yellow. And if it's a full electron, it should look red. And if it's a full hole, it should look blue. Okay. So let me start with this state, which is deep inside the junction. It's a superposition of electron and hole. It looks yellow. And let me move, and because it's dispersive, it should move along the junction and eventually it should move outside of the junction. And I can model that situation by increasing W, which is the width between the SNS interface. So I will run a simulation and you trace this state adiabatically and see how it behaves. So it will turn from yellow to red. So that's telling you that if you're an Andreev state associated with a convex critical point, as you move outside of the junction, you will turn from an Andreev state to a purely electronic state. And you can play a similar calculation for a concave critical point, and that and in contrast to the electron-like Andreev states, this state would convert from an Andreev state into a purely hole-like state as it moves out of the junction. So the upshot is that if you bias voltage in one direction, so you attach two leads to the junction, you bias voltage in one of the leads. So if you have positive bias voltage, you're pumping in some electrons. If you have negative bias voltage, you're pumping in some holes. The number of electrons and the number of holes that can go through would depend on how many convex and concave critical points you have. This is a situation that is similar to Landauer transport in 1D. So this is kind of like a 1D quantum wire, but it's not a quantum wire of electron. It is a quantum wire of Andreev states, and it's a quasi 1D state localized at the SNS interface. So deep inside the junction, it's really a superposition of electron and holes because of superconductivity. But as it moves out of the junction, moving into the normal leads, it turns either into an electron or a hole, depending on whether the Andreev state is associated with convex or concave critical points. So by doing a Landauer transport type of experiments in a superconducting junction, if you have positive bias voltage, you will measure a slope that probes the number of convex critical points. If you have negative bias voltage, you will have a slope that probes the number of concave critical points. So assuming there's no disorder, no backscattering, everything is transparent, then a generalization of Landauer transport would tell you that you can probe number of convex concave critical points on the Fermi surface for the 2D electron gas underneath this junction. And this actually also tells you there's a rectification effect, because if you pump in some AC bias voltage and try to drive some currents, then you can actually get a net DC current that is quantized to the order characteristic of the 2D Fermi sea. What I gave you is just some, I know I'm running out of time, so I'm going to end soon. I just gave you some hand-wavy argument of why there can be quantized transport phenomena sensitive to Fermi sea topology. In some follow-up work with Christophe Debut, we did some a numerical simulation using Quant. It's a nice Python package which allows you to do quantum transport simulation. We can study a simple, say, for example, a simple tight binding model, an isotropic tight binding model, such that when you change the chemical potential, you can go from an ellipse-like electron Fermi pocket to a annulus Fermi surface, a Fermi sea, and then to this hole pocket. So the order characteristic would change from +1 to 0 to -1. And you can do a quantum transport calculation and measure this GQ1 numerically. And you indeed see that in different region, you have this different rectification effect and different quantized plateau, which very much look like what you have in quantum wire transport. But here, it's really probing a 2D topological invariant. And what is more nice about doing numerics is that you can study not just the linear junction, where our theoretical analysis begin with. You can also study point contact. And if you study point contact, you will screw up the quantization in G21 But surprisingly, we see that if you look at the rectification effect, it's still robust. If you look at the biased asymmetric part of G21, you will still be able to probe the Fermi C order characteristic of the underlying matter. So that is some maybe some higher order topological, slightly higher order in our understanding that I'm happy to share more if you're interested. I can talk about it offline. So and just for the fun of it, we also did a numerical simulation for the case with bilayer graphene, Bernoulli stacked bilayer graphene. So it's not, the unit cell is not too complicated, just 4 orbitals. Interesting thing is that as you tune the displacement field, you can realize these 4 types of Fermi C topology. This is a band theory calculation of, in what so as you change displacement field and overall chemical potential, you can realize in different parameter regime, different Fermi C topology. This is just band theory, simple calculation. And next, I'm going to show you what happens when you calculate delta G21 by doing a numerical quantum transport simulation. That is what you will see. And indeed, in the regime where you have topology 1, you will measure a roughly quantized delta G21. So you can use a topological rectification effect to study Fermi C topology. Yeah, just a demonstrating example using Bernoulli stacked bilayer graphene. Yeah, with that, I would like to. I know I'm running out of time, so I'll just stop here with the summary that today I introduced 2 kinds of quantized transport effect by bringing together 2 ingredients: topology and superconducting proximity. In the first part, here, I actually studied fractional quantum Hall edge states proximatized by superconductor. We realized there is a family, an infinite family of superconducting edge phase that arises due to counterpropagating edge modes plus superconducting proximity disorder, 0 mean random disorder in the pairing proximity. It gives rise to a family of new fixed points which have interesting quantized transport signature. In the second part, I talked about Fermi C topology. So it's a non-interacting system, and in the absence of disorder, you can study bulk proximity, leading to interesting long local transport that is quantized and Fermi C topology. Yeah, with that, I would like to end here. I don't have time to go to some other parts which is related to Fermi C topology probed in other contexts, but I think I also mentioned that briefly 5 months ago, and I'm happy to chat more about that offline. With that, I would like to thank you for your attention. I'm happy to take more questions.
So in the second part of
Yes.
the talk, I guess the first part of the slide,
Yes.
you mostly focused on sort of, at least the pictures were sort of non-interacting particles.
Yes.
How do interactions affect this
Right.
story?
I don't have a very careful treatment to clarify that matter, but I think to leading order, I expect not much would change because the whole system actually have a gap. So the presence of these Andreev states is protected by the bulk superconducting gap. So if I only have an infinitesimal amount of interaction, it shouldn't change the presence of these Andreev states, and also shouldn't change whether they are electron-like or hole-like. Yeah. So at least in the rectification effect should be there. I expect I don't know how confident I really am, but I would expect that the quantization wouldn't change much, at least to leading order. Yeah.
Yeah, for your fractional quantum Hall segment, when you were talking about edge
Yes.
modes, I guess for this filling factor and the scenario you were discussing, you have like a charged edge mode, right?
Yes.
You also mentioned for certain filling factors, you could have Majoranas.
Yes.
So I'm curious, this gets tricky because I guess Majoranas are charge neutral.
Yes.
So is there like a similar clever experimental design you can make to measure Majoranas in these different filling factors?
Okay. So the thing is this. So indeed, the Majorana is neutral, but as Professor Levin can explain that better than I do, so let me go to the here. The electron, the edge electron operator, the local electron that you can create out of the these modes would involve the Majorana. So it's the Majorana times some e to the power I phi. Okay. So when you introduce pairing or backscattering, the Majorana is playing a role there. So the Majorana affects the electrical transport both with or without superconductivity, because the electron operator carries information of the Majorana fermion field. So when in the superconducting generalization of what I talked about here, for Pfaffian, anti-Pfaffian, particle Pfaffian states, you would consider pairing operators, not just the neutral backscattering that Professor Levin considered, but also pairing operators, the tunnel Cooper pairs in and out of the edge. And that operators would involve the Majoranas, and you do the disorder algae flow analysis, and you will see some of the modes are not averaged out. Some of the modes are remaining and contribute to transport. The information of Majorana is there. Yeah. So it's not just that it's neutral, so it does not contribute to transport, but the Majorana field is intimately tied to the electron operator, where all the local physics concerns. Yeah.
Okay. Yeah.
So.
A naive question on your second part of your topic.
Yes.
So you're talking about transport through a narrow channel between the two superconducting
Yes.
islands. But can the electron just go through the superconducting islands?
Yeah, this is a great question. So, okay, I think I can explain that maybe just with that. So indeed, when I bias V1, a lot of the currents actually would go into the superconductor. But maybe I didn't explain that in great detail here. But the experimental observable that we want people to measure is this guy. So it's a non-local conductance. You bias voltage in lead 1, you collect currents in lead 2. We also need to ground the superconductor. So the process that Professor Song you mentioned would occur. A lot of currents will go into the superconductor, but these are not the currents that will be collected by lead 2. As you bias V1, the only currents that will flow into lead 2, assuming that the superconductor is wide enough, would be the currents that go through this narrow channel, become the Andreev states, move along the junction, and turn back into either an electron or a hole, depending on the Fermi surface critical point nature. And I2 is quantized in that sense. Yeah. So a lot of currents would flow into the superconductor, but they flow to the ground via the superconductor. As long as lead 1 and lead 2 are far away enough, the only additional currents that flow into lead 2 is via these Andreev states. Yeah.
Okay, if there are no more questions, let's thank folk again.